In this problem, we're going to evaluate the equilibrium between H2 and F2 gases and their product 2HF. The equilibrium constant, in terms of concentration, for this reaction is 1.0 times 10 to the 2, or 100, which is rather large, suggesting that by the time equilibrium is reached, there will be a lot of products and comparatively few reactants. But we will have some of all three left over. If we start our reaction with 0.1 molar H2 and F2, we would like to know how much of all of these components we'll have by the time we reach equilibrium. Remember that this reaction does not go to completion, meaning that there will be no limiting reactant, and we cannot do direct stoichiometry to figure out the answer to this problem. Instead, we construct an ice table. We think about what we know about initial conditions, I, how conditions change, C, and ultimately how those conditions arrive at equilibrium, E. To fill in the ice table, we think about the information we're given. Initially, we're told that the reaction is begun with 0.1 molar hydrogen and 0.1 molar fluorine, so we can fill in our ice table with those quantities. If our reaction is beginning with these quantities, then the implication is that we have not produced any product yet. So initially, at the start of this reaction, because we didn't introduce HF explicitly, we have 0 of it before a reaction begins. As our reaction proceeds, though, we expect that, based upon our initial conditions, we'll produce products and consume reactants. That means that our reactants will change by decreasing. How much will they decrease? Well, we don't know yet, so let's leave that variable, x. And because we have a stoichiometric equivalent amount of both hydrogen and fluorine, we expect both hydrogen and fluorine's concentrations to change by an equivalent amount. Our hydrogen fluoride product, however, will increase in concentration, so its change is positive. And stoichiometrically, there's twice as much hydrogen fluoride produced as either hydrogen or fluorine consumed, so its change will report as 2x. To get our equilibrium concentrations, we'll just add down this column. For our equilibrium amount of hydrogen, we expect 0.1 minus x. Likewise, for our equilibrium concentration of fluorine. For our equilibrium concentration of product, we'll expect 0 plus 2x. Our goal is now to solve for x. How do we do that? Well, we take advantage of what we know about our equilibrium constant and the expression that describes it. We know that our equilibrium constant could be expressed in terms of products and reactants. Here, that equilibrium constant expression looks like the concentration of HF squared divided by the concentration of H2 and the concentration of F2. Remember that an equilibrium constant is only applicable at equilibrium, and we have information about equilibrium in this ice table right here. So, let's start plugging in this information and what we know about our equilibrium constant's value into the expression that we've written down below. We know that the value for the equilibrium constant is 1.0 times 10 to the 2. We know that at equilibrium, the concentration of HF is 2x. And our equilibrium constant expression tells us we have to square that concentration. Our concentration of H2 at equilibrium is 0.1 minus x. And our concentration of F2 is likewise 0.1 minus x. Now, we need to solve this single equation for one unknown. How do we do that? Well, we need to employ the quadratic equation. To simplify this expression down, I'll multiply through the denominator on the right-hand side and square the numerator. We'll end up with 1.0 times 10 to the 2 is equal to this quantity squared, 4x squared, divided by this quantity in the denominator down below. We'll FOIL things out and we'll end up with 0.0 minus 0.20x plus x squared. To simplify this further, I'll multiply both sides of this equation by the entire quantity in the denominator on the right-hand side. We'll end up with 1.0 times 10 to the 2 multiplied by 0.01, which gives us simply 1.0. We'll multiply 1.0 times 10 to the 2 by negative 0.2, which gives us 20. We'll multiply 1.0 times 10 to the 2 by x squared, which gives us positive 100 x squared. All of that's equal to 4x squared. To set up a quadratic equation, we'll make the right-hand side of this equation equal to 0 by subtracting 4x squared from both sides. Subtracting 4x squared from both sides leaves us with 96x squared on the left-hand side, 20x, and positive 1.0. Now, we have to remember our quadratic equation. A solution to a quadratic equation is negative b plus or minus the square root of b squared minus 4ac all over 2a, where this quantity, 96, is a, this quantity, negative 20, is b, and this quantity, positive 1, is c. We'll plug into our quadratic equation. X is equal to positive 20 plus or minus the square root of negative 20 squared minus 4 times 96 times 1.0, all divided by 2 times 96. In solving this equation, we come up with two roots. X is equal to 0.125, or x is equal to 0.0833. I've moved those two solutions up near our ice table so that we can evaluate why there are two and whether we should have two. So, x is a solution to this ice table's unknown change. Suppose that x were 0.125. What would the equilibrium concentration of H2 be, and what would the equilibrium concentration of F2 be? Well, to solve for those concentrations, we'd take 0.1 and subtract from it 0.125. We'd end up with a number that is negative. What physical sense does a negative concentration have? It doesn't have any real physical meaning. Therefore, we reject this result. We reject the result 0.125 because it's physically unrealistic. It results in something that doesn't make any sense. The only possible valid solution to this problem is that x is equal to 0.0833. Because when we subtract 0.0833 from 0.1, we get a positive value. So, how do we determine our concentration of H2 at equilibrium? We do just that. And it turns out that this also equals the concentration of F2 at equilibrium to two significant digits, 0.017 molar. We solve for F2 in the same way. To solve for our concentration of HF at equilibrium, we multiply our solution by 2. And we end up with 0.17 molar. In this way, we have solved for the equilibrium concentrations of all of our reactants and our product.